In part 3, we saw that water stores energy, buffers temperature changes, and reshapes atmospheric radiation through humidity. Now we go one step further. Water does not only store energy, it transports enormous amounts of energy through the atmosphere every single day, across continents, upward into the atmosphere, and eventually back toward the surface. Climate is not only about radiation leaving the planet, it is also about how energy is transported inside the atmosphere. Energy reaches Earth primarily as solar radiation. When this energy reaches oceans, lakes, soils, and vegetation, a large fraction does not directly warm the air. Instead, it evaporates water. The energy used in evaporation is called latent heat. Unlike sensible heat, latent heat does not immediately increase temperature. Instead, it is stored as potential energy associated with the separation of water molecules during evaporation. This process occurs everywhere on Earth, not only over oceans but also over land through evapotranspiration, the combined process of evaporation from surfaces and transpiration from plants. Globally, this latent heat flux averages around 80 watts per square meter, making it one of the largest energy transfers at Earth's surface. But the story does not end here, because water begins to move. Warm, moist air is lighter than cold air, so it starts ascending. As it rises, atmospheric pressure decreases and the air expands. As air expands, it cools. This behavior follows the basic gas laws governing pressure, temperature, and volume in the atmosphere. In dry air, the temperature decreases by roughly 9.8 degrees Celsius per kilometer or 28 degrees Fahrenheit per mile. This is called the dry adiabatic lapse rate. As temperature drops, saturation humidity becomes lower, so the ability of air to hold water vapor decreases. Eventually, air becomes saturated, and water vapor condenses into cloud droplets or ice crystals. When this happens, the latent heat stored during evaporation is released into the atmosphere. This released energy partially offsets the cooling caused by expansion. As a result, moist air cools more slowly with altitude than dry air. This produces the moist adiabatic lapse rate, typically between 4 and 7 degrees Celsius per kilometer or 11 and 20 degrees Fahrenheit per mile, depending on temperature and humidity. Energy absorbed at the surface is therefore transported upward and released higher in the atmosphere. Latent heat is not a minor effect. It is one of the main engines of atmospheric motion. Temperature strongly controls how efficiently energy can leave Earth as radiation. According to the Stefan Boltzmann law, radiative emission is proportional with the fourth power of temperature. This means that even moderate cooling can significantly reduce the amount of radiation emitted. But radiation is not the only way energy moves through the atmosphere. Heat exchange between air and particles can also occur through conduction and convection, processes often described in simplified form by Newton's law of cooling. These processes depend mainly on temperature differences between air masses, rather than the absolute temperature raised to the fourth power. And unlike radiation, convection transfers heat between all atmospheric gases, including nitrogen and oxygen that make up most of the atmosphere. Because of this, energy stored in water vapor is not immediately lost to space. Instead, a large portion continues to move through the atmosphere via convection and large-scale circulation. When water vapor condenses, clouds form. Clouds play a crucial role in Earth's energy system. In addition to the latent heat released by condensation, cloud droplets and ice crystals absorb some of the incoming solar radiation from above and infrared radiation emitted by the surface from below. And this energy is not small. Through turbulence, molecular collisions, and convection, much of this absorbed energy is redistributed to the surrounding air. In this way, clouds act as powerful energy exchangers inside the atmosphere. Instead of energy remaining confined to specific absorbing gases, part of it becomes distributed throughout the moving atmosphere. This process spreads heat across the atmosphere and contributes to large-scale circulation patterns. As warm, moist air rises, water vapor starts condensing and releases the latent heat absorbed during evaporation. Clouds form, and they absorb some of the solar radiation. Clouds and greenhouse gases, such as carbon dioxide and water vapor, also absorb part of Earth's infrared radiation. The atmosphere does not consist mainly of greenhouse gases, but nitrogen and oxygen. These gases interact only weakly with Earth's infrared radiation compared to greenhouse gases, so their radiative absorption is low. However, through molecular collisions and convection, latent heat released by condensation and energy absorbed by greenhouse gases and clouds quickly spread throughout the surrounding air. Because nitrogen and oxygen are so abundant, most of this energy coming from absorbed radiation and thermal energy is transferred to these gases. But air can ascend high into the troposphere. At these altitudes, air becomes thinner and molecules are farther apart. Under these conditions, convective heat transfer becomes progressively weaker as air density decreases and radiative processes begin to dominate. Infrared active gases, including water vapor and carbon dioxide, can then emit part of their energy into space. The radiative efficiency of nitrogen and oxygen in the infrared is extremely weak because their symmetric molecular structure does not produce strong infrared absorption bands. As a result, most of the transported energy remains within the atmospheric system until it can eventually be emitted by infrared active gases. As we saw earlier, when moist air ascends, it cools at the dry adiabatic rate until it reaches its saturation point. After condensation begins, the temperature decrease becomes slower because latent heat partially offsets the cooling. However, air that rises in one region eventually descends somewhere else. When descending air moves toward lower altitudes, atmospheric pressure increases. According to the same gas laws described earlier, this compression warms the air adiabatically. As temperature increases, the air's capacity to hold water vapor increases. However, much of the water vapor already condensed during the earlier ascent, so the remaining moisture content is relatively low. As a result, while the saturation level rises, absolute humidity remains low, producing very low relative humidity. Because condensation released latent heat during the earlier ascent, the air mass lost less energy while rising than a completely dry air mass would have. Much of this released energy was rapidly shared with the surrounding atmosphere through convection and molecular mixing, remaining within the atmospheric circulation. As a result, moist air cools more slowly during ascent, while descending air later warms at the dry adiabatic rate, which increases temperature faster. Radiation increases rapidly with temperature, so this warmer air can emit more radiation. Some of this radiation escapes to space, but some of it interacts again with the surface and the atmosphere. As the air approaches the surface, a larger portion of this radiation can interact again with the surface and the lower atmosphere. As a result, the transport of latent heat does not only influence the gases that absorb radiation directly. Through atmospheric motion and mixing, it affects the temperature structure of the entire atmosphere. Some researchers have explored alternative ways of describing the radiative balance of the atmosphere. One example is the work of Hungarian atmospheric physicist Ferenc Miskolci, who was previously working for NASA. He analyzed long-term radio sonde data and suggested that the overall infrared optical thickness of the atmosphere remains remarkably stable. His hypothesis proposed that increases in carbon dioxide could be partially offset by changes in atmospheric water vapor. This idea remains debated and is not part of the mainstream climate framework. However, it highlights an important point. Water vapor is not passive. It responds dynamically to temperature, circulation, and humidity changes. Understanding climate therefore requires examining the full energy cycle of radiation, moisture, and atmospheric motion. Radiative forcing matters. Latent heat transport matters. Convection matters. And water connects them all. This leads to an important implication. The amount of water entering the atmosphere does not only influence humidity, it also determines how much energy is transported through the atmosphere by latent heat. In other words, the hydrological cycle is also an energy transport system. And over land, a large fraction of that water does not come from the oceans, it comes from vegetation. In the next part, we turn to a factor that is often underestimated in discussions about climate. If vegetation controls large parts of evapotranspiration, then it may also influence how energy moves through the climate system. And that leads to an important question. How does vegetation influence climate change? From the next part, we begin exploring uncharted territory within the boundaries of widely accepted science. The role of vegetation will be in focus, which is often neglected regarding climate change. We will see if it simply adapts to climate change or actively influences it. If you liked this part, don't forget to like the video and subscribe to the channel so you don't miss the next part and other exciting videos being released in the future.